Hello everyone, I hope you are doing well. So in today's video, we'll be going through the 2022 physics exam part 1 of the short answer questions. We'll be going through questions 1 to 10. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Figure 1 shows 4 positions, 1, 2, 3, and 4 of the coil of a single turn, simple DC motor. The coil is turning in a uniform magnetic field that is parallel to the plane of the coil when the coil is in position 1, as shown. So when the motor is operating, the coil rotates about the axis through the middle of the side LM and NK in the direction indicated. The coil is attached to a commutator. Current for the motor is passed to this commutator by brushes that are not shown in figure 1. Basically, there's current. They're telling us. All right. So when the coil is in position 1, in which direction is the current flowing in the side KL? Is it from K to L or from L to K? Okay, let's have a look at position 1. So basically, if we want it to rotate clockwise, on the side KL, there must be a force going up for it to rotate, clockwise. And so basically, using your right hand slap rule, we know our palm represents our force. So your palm should be up. Your fingers are going to be representing the magnetic field, which is to the right. And so your finger, or your thumb in this area is your current. And so basically doing that, you should realize that your current direction should be this way. And so basically, on the side KL, it's going from K to L, basically. So K to L is the direction of current. So basically, we knew the how. So we knew the force is up on the side, basically KL. So using right hand slap rule, right hand slap rule. I think that's basically what you just need to justify. So we said the answer, we've said how we did it, so we knew the force has to be up on that side and using the right hand slap rule, and yeah, to get our direction of the current. Beautiful. Question B. When the coil is in position 3, in which direction is the current flowing in the side KL? Is it from K to L or from L to K? Let's have a look at this. So in position 3, the actual coil has rotated 180 degrees. And basically, remember, it's going through a commutator. And what is the definition of commutator? We know that the commutator, what it does is that every 180 turns, it reverses the current direction to, make sure continuous rotation happens. So on this side KL, basically this side here, we knew that initially the current was going this way, from this. But now it's going to go the opposite way because it's rotated 180 degrees. So it should go to the side L to K. Now, we can also make sure, we are 100% sure about this. So basically, one way to also do this is it's still rotating clockwise. So the force on KL on this side has to be going down. And again, using your right hand slap rule, your palm is your force. Your fingers are going to go to the right. And so your thumb should be going to basically this direction. So it is on the side L to K. But it's only 1 mark. So I think you just need your answer basically. So L to K basically. C. The side KL of the coil has a length of this and experiences a magnetic force of this due to the magnetic field, which has a magnitude of this. Calculate the magnitude of the current in the coil. Beautiful, easy question. So we know that force is equal to your number of turns, your length, basically your length, times your current, times your magnetic field strength. So we know that it's a single loop, so that's 1. So basically, our force, what was our force actually? So it's 0.15. Your N is 1. Your length of the wire is 0.10. We're trying to calculate the current, and we know that the magnetic field is 0.5. So dividing, basically, it's going to be 0.15. It's going to be 0.10 times 0.5. It's going to be 3.0 amps, basically. Done. That's the current that's going to run. Question 2. There are over 400 geostationary satellites over the Earth in circular orbit. The period of the orbit is 1 day. is it supposed to say in 1 day, is this. Each geostationary satellite remains stationary in relation to a fixed point on the equator. Figure 2 shows an example of the geostationary satellite that is in orbit relative to a fixed point x on the equator. Explain why geostationary satellites must be vertically above the equator to remain stationary relative to the Earth's surface. Let's really have a look at this. So, I'm going to draw a nice diagram here, and I'm going to go into depth and why we have to rotate in that equator. So, let's say this here is our equator, basically. So, in a 3D model like that. Looks nice. Okay. So, we know the center. Imagine this is a 3D model of the Earth. And so, basically, if this is our equator, and we know, let's say it rotates this way, like basically, and so we're rotating with the equator. Say you have a satellite and it's on the equator. Why do we put satellites on the equator if we want it to be geostationary? First of all, they will have a force that will be, the centripetal force is going to be towards the center of the Earth. So that's great. So the force is basically, towards the center of the Earth. That's a good thing. And also, it's going to move relative to the axis. So you know how the Earth's rotating around the equator? So it's rotating, the Earth's rotating with the equator. And so also this is going to also rotate with the equator itself. So basically, someone who's watching this is going to see this satellite. And because he's rotating with the Earth, and the satellite is also rotating with the Earth, he's going to see it and he's going to be like, damn, this is stationary. Like, it's not moving. It doesn't look like it's moving because he's moving relative with it. So that is why, for conditions for it to be a basically, why it has to be on the equator. Now, let's understand, okay, why not put it on the equator? Let's think, why not? A lot of students might be like, okay, why can we not put it, say, how the Earth's, why can't we put it on top? So let me just draw another part here. So let me draw this. Why can I not let it, let's say we want it to rotate this. You know how the Earth's pretty much is rotating? Basically this way. So the Earth's rotating. And so why cannot this rotate this way? Why can we not put it on the equator, but a little bit up, above the equator? Now that's a problem. For it to rotate in the same, axis of the Earth, the force, pretty much the centripetal force must be directed towards this center. But that's false. We know that the centripetal is, the actual center of the Earth is in the middle. So what's the problem? So the force is going to go like this, basically. And so what's going to happen is it's going to actually go down. And this is not going to be stationary. So if someone who's watching it on the Earth, he's going to look at it and he's going to be like, why is it moving? This is not, stationary. So it's not a geostationary satellite. So that our conditions are not being met. Then, okay, another fixable point someone can say is, why not do this then? Why not put it, what the hell was that? Why not put it on basically on this, why not put it at what happened? So why not put it basically on, so at an angle. So at a, let me try to get it nicer. So like that. Basically, let me move this there and basically move there. So why not put this at an angle? So why don't we put something why don't we let something rotate at an angle, basically? So let's say we put a satellite and it rotates at an angle, pretty much at an angle of the equator. Why can't we do that? Because now we fixed the force. The force is going to be towards the center always. So if it's here, it's always towards the center. Now there's a big problem with this. Basically, so you remember for a geostationary, it must be relatively stationary when someone's looking at it. So basically, if someone's watching it, because he's rotating with the Earth, the equator of the Earth, basically, he's moving to the right. This here is going to be moving also, let's say it's moving this way. While he's looking at it, he's going to see it going up and down, up and down. So it's not also going to be stationary. So basically, for all conditions to be fixed, it must be on the equator. Because, here it is nicely, another overall description. If you have basically, now look at this. So if you have a satellite, we can see that the force is going to be always towards the center. Always. Basically, that's fixed. And it's going to be rotating basically perpendicular to its motion. So it's going to be it's going to be in a circular path, basically. And basically that's it. So it's always going to be rotating in the axis of the Earth. And so it's going to be rotating at the same rate as the Earth is. And so it remains stationary, basically. Now that makes more sense. It's a very hard question to really explain, but I think that's a good basic explanation. You don't need a lot. It's only 2 marks, so I don't think you need to write crazy a lot, but basically just 2 conditions. So we know that the centripetal force must be always directed towards the center, and also the satellite must orbit in the axis of the Earth for it to remain geostationary. All right. So let's write that. So let's say the central pitot force must be directed towards the center of the Earth. So that's one condition. And also the satellite, I don't know, I think I spelled that wrong, but who really cares? So the satellite must orbit in the same axis, so in that same axis, in the same axis as the Earth. And that's it. These are your 2 conditions that must be met for pretty much why a geostationary satellite has to be in that equator, basically, to remain stationary. Easy. B, using G as that, the mass of the Earth is that, the radius of the Earth, show that the altitude of the geostationary satellite must be equal to this. Beautiful and easy question. So let's have a really nice drawing of what's happening. So let's say this is our Earth, and basically this is our satellite. Now, what we're trying to prove is we're trying to prove the altitude. So you remember the altitude is the center of that satellite to the surface of the Earth. That's your altitude. We're basically trying to prove A, in other words, this altitude. And so I would use Kepler's law. Remember Kepler's law, and I would try to calculate your R, because your radius, what it's going to give me, it's going to give me the actual radius pretty much to the center of the Earth and to the center of the planet, because we both have its period. We actually have its period. So I would use Kepler's law, basically. So let me use Kepler's law. So Kepler's law, looking at my summary sheet, let's have a look at there. So, okay, here is Kepler's law. So it is R is equal to cube root of, so R is equal to cube root GM T squared over 4 pi squared. So that's going to be what? All right, so that's going to be, G is what? 6.67 times 10 to the negative 11. Your mass of the Earth is 5.98 times 10 to the power of 24. Your period, what was our period? They did tell us 86400. So 86400 squared. And all divide that by 4 pi squared, basically. So that's going to give us our radius, basically. Done. Let's use our calculator. Times 10 to the power of 24. 86400 squared. 4 pi squared. And that gives me basically 4225. I'm going to write the whole thing. 047 4.31 meters. And that's going to give that's the radius, this R radius. If I wanted this altitude, all we have to do is minus the radius of the Earth from the R value, and it's going to give me your altitude. So basically the altitude is your 42250 474.31 minus your radius of the Earth, which is 6.37 times 10 to the power of 6. And that's going to be what? 6.37 times 10 to the power of 6. That's going to give me basically 3.59. Yes, 3.59 times 10 to the power of 7. So we've shown it, basically. We've shown that's our altitude. Done. So we've proved it. Beautiful. So C, calculate the speed of an orbiting state geostationary satellite. Easy. So we know to calculate the speed, it's just going to be the square root of GMR. So we know in this case, what is our G value? Basically, our G value in this question is, G is 6.67 times 10 to the negative 11. Your mass of the Earth, basically, you remember your big M is the mass of what's orbiting. It's that Earth. It's orbiting the Earth, your big M. And we know it's 5.98. So 5.98 times 10 to the power of, 9 times 10 to the power of 24. Divided by radius. So the radius of the whole from the centers, between the centers, which we calculated, didn't we? Yep, this here. So which is, wow, it's 4225. So 4225, 04704, 74. Is that right? So 7431. Put that in my calculator and I should get the answer. It's a very, very big answer, but yeah, it's 6.67 times 10 to the negative 11. And so 5.98 times 10 to the power of 24. So 422504. 74.31. That gives me to three significant figures, 3.07 times 10 to the power of, so 1, 2, 3. 3. Is that right? 1, 2, 3. Yep, that's it. Beautiful. Next question. Question 3. A schematic diagram of a mass of a spectrometer that is used to deflect charged particles to determine their mass is shown in figure 3. Positive singly charged ions with a charge of this are produced at the ion source. These are accelerated between an anode and a cathode. The potential difference between the anode and the cathode is 1,500 volts. The ions pass into a region of uniform magnetic field B and are directed by the field into a semicircle path of diameter D. Alright, calculate the increase in kinetic energy of each ion as it passes from the anode and the cathode. Give your answer in joules. Beautiful. So, to calculate the kinetic energy, what do we know? Basically, looking at my formula sheet, we know that work, let's have a look at this. Okay, we basically know that work is equal to your change in kinetic energy, which is, an increase in kinetic in this case, is equal to QV. Basically, we're just trying to calculate what's Q. It's 1.6 times 10 to the negative 19, it said. Was that right? Yep. Times your voltage, which was 1,500. Let me check that again. Yep. So putting this 1.6 times 10 to the negative 19 times 1,500. That's going to be 2.4 times 10 to the power of negative 16. Done. Each ion has a mass of 4.8 times 10 to the negative 27 kilograms. Show that each ion has a speed of this. When it exits the cathode, assume that the ion leaves the ion cells with a negligible speed. Show working out. Beautiful. So we know our change in kinetic energy, which we just calculated, is equal to your half mv squared, your actual kinetic energy formula. So we calculated it to be, your change in kinetic is 2.4 times 10 to the power of 6. So what was it? Negative 16. What am I doing? Negative 16. Did I write it right? Yep. And that's going to be equal to your half. What's our mass? So 4.80 times 10 to the power of negative 27 velocity squared. So we're just going to calculate the velocity in this case. Yeah. So I'm just going to do it. So velocity is basically the square root of 2.4 times 10 to the power of negative 16 all over 4.80 times 10 to the power of negative 27. Did I do any mistakes here? So 2, yep, makes sense, divided by that. Beautiful, so let's check that. 2, that. 4.8 times 10 to the negative 27. That gives me, basically, your velocity is 3 point, we're just trying to show it's the same. It is the same. So 3 point, yep. Basically 1/6 times 10 to the power of 5 meters per second. So we've shown it. That's it. Next question. The region of the uniform magnetic field B in figure 3 has a magnitude of this. Calculate the diameter D of the semicircle pathway followed by the ions within the magnetic field. Easy. Now we know how to calculate the radius, basically. So our radius is going to give us, basically, this over here. it will give us this, basically, this distance here, that radius, which is r. If we want the diameter, it's just doubling the radius. So let's calculate the radius. We know that the radius is just mv over qb. And so your mass, they told us the mass, where was it? 4.8 times 10 to the power of negative 27 times your velocity, which we're going to use their velocity, to be honest, 3.16 times 10 to the power of 5, all being divided by your charge, which is 1.6 times 10 to the negative 19, and your magnetic field, which is 0.10. Now, I'm just kind of concerned, should I use my actual velocity on my calculator, which is the exact value? Of course, you should use that. I don't think, I'm just going to be safe with it. So I'm going to write this whole exact, so 16 on my calculator. So 227.76 basically squared. What am I doing squared? What's squared? Yeah, so that's going to give me, so it's going to give me 4.8 times 10 to the power of negative 27, 1.6 times 10 to the negative 19, times 0.1, and I got the radius to be 0.0948 meters. And of course, we're going to double our radius to get our diameter. So our diameter is basically timesing this by 2. And so, to how many significant figures? We want 2. So basically, it's 0.19. So 0.19. Done. Beautiful. Question 4. A square loop of wire connected to a resistor R is placed close to a long wire carrying a constant current in the direction shown. So remember, when there is a current carrying wire, we know that there's going to be a magnetic field produced, and we can determine that magnetic field that's produced using our right-hand group rule. So the square loop is moved 3 times in the following order. So movement A, which is starting in position 1, okay, so it's there in figure 4, and the square loop rotates 1 full rotation at a steady speed about the x-axis. All right, the rotation causes the resistor R to first move out of the page. Beautiful, makes sense. So this thing is just basically rotate, like this here thing, it's just being rotated. So in movement B, the square loop is then moved at a constant speed parallel to the current carrying wire from position 1 to position 2. So it's basically moved down. And in movement C, the square loop is moved from a constant speed to perpendicular to the current carrying wire from position 2 to position 3. So basically to the right. Complete the table below to show the effects of each of the 3 movements by sketching an EMF generated in the square loop during the motion of the axis provided. Scales and values are not required. Stating whether any induced current in the square loop is alternating, clockwise, anti-clockwise, or has no current. The way you determine the induced current is by using Lenz's law. We know that. And so for one, so sketch an EMF generated in a loop during the motion. So I think, yep. Okay. So movement A, rotation about the x-axis, and we have to draw first let's draw the EMF for it. Let's basically look at this. So we know using a right-hand group rule, imagine group that wire, we're going to know straight away that we're going to have magnetic field lines basically coming into the page here. There's going to be magnetic field lines that are coming into the page in this direction. And so I'm just going to basically duplicate these. I'm going to duplicate these. I have what they basically look like. Basically like that. And so you can see that initially let me a little bit move them up. So initially what's happening is they are into the page. So let me draw a nice magnetic flux diagram because it's so easy. When you draw a magnetic flux diagram, then basically then you can easily draw, you're changing magnetic flux, you can easily draw a EMF. So let's have a look. So basically, the fields are all inside of it. It's all inside that loop. So the flux is at its maximum at first. So as the loop kind of rotates around the axis, it's gonna go down. And in that rotation, like halfway, quarter of a rotation, then it's gonna be 0 because the field lines are not gonna be passing through it. And then it's gonna be passing through the other direction. So they're gonna increase in the other direction. So basically, this is how overall what you should realize. For one full rotation, it's basically gonna look like this. And so now it's easy because now you can easily determine how your EMF is going to be generated. Basically, EMF, we know that EMF is negative N. You don't even need that N, by the way, but yeah, so negative change in flux over change in time. Basically, it's this here, it means your gradient of this line. So, have a look at the gradient. So we can see that, first of all, any turning points are going to be your zeros. So this has a turning point here, it's going to be here. This turning point is going to be 0. It's going to be at your x-intercept, your t values. So we know, let's have a look at the gradient from here to here. We can see that it's decreasing because it's going down. So this here is going to go negative. It has a negative gradient. But because what Faraday's law says, if the gradient in this case is negative and it's going to be multiplied by another negative, so it's going to be positive. So it actually has to be above. Basically, it's going to have like this, a shape of like this. Can you see how it's a positive EMF that's going to be generated? And so let's look at the other part. So here then it's going to be positive because it's increasing. Now, if your gradient's increasing, which is positive, it's going to be multiplied by the negative, so it's going to be overall negative. So it's going to be below. Oh, it's not that nice, but basically it looks like below. That's it. So basically your EMF that's going to be generated, let me rub this garbage out. So basically your EMF that's going to generate looks like this graph, a basic sine graph. If you do methods, you know how to do this in a second, basically, because basically it's just, we originally had a cosine graph for our, cosine graph, and then you just derive it, which is basically negative sine t. And then you put a negative, so it's going to be basically a positive sine t. So this is a sine graph right over here. That's only if you know methods. So it's very easy to do physics with methods, basically. But yeah, that's how you would do it. So let's sketch that as our EMF. So basically it will look like this. So let me just draw it nice. That. And basically like that. Wait, let me just take this here, duplicate it. Rotate it a little bit like that. So let me rotate with my hands. Oh my god, I feel like that's a lot of work, but nearly there. So if I a little bit make it smaller. Right, like that. There we go. That works. That's perfect. So there we go. Let me draw those. And that's it. That's how your EMF will look like. And so the next question says, direction of any induced current, alternating, clockwise, anti-clockwise, or no current. So let's have a look at this. Basically, it's useless to look at the EMF. I always try to look at the, let's rub this up. What was the actual, basically, what was our flux diagram? So we knew our flux diagram looked like this. We know our flux diagram looked like this. So basically our flux diagram is going to tell us how the current's going to be induced. Basically, we started at maximum flux. Let me write that. So we started at maximum flux and then we approached 0. So what's happened is that there was a decrease in flux in that quarter of a turn. So when there was a decrease in flux, we know that by Lenz's law, that the induced magnetic field will be in the same direction. And so imagine using your pretty much your right-hand grip rule. So make sure your thumb's into that page. You would see that the current will be directed to basically clockwise from basically this part here. But then look at the problem. Then you got another part. So now it's at 0 and it's going to be increasing, but in the opposite direction. So there's an increase in flux. And we know that when there is an increase in flux, there'll be an induced magnetic field in the opposite direction. So imagine using your right-hand grip rule, but your thumb's going to be out the page. Basically, it's going to go anti-clockwise now. So sorry, it was clockwise. Basically, it was clockwise at first. Yep. Then it's going to be anti-clockwise. So it's alternating. Pretty much it's alternating. It's not a constant value. And again, it's going to happen again. You're at its maximum and you're going to go back to 0. And then you're back to 0 and you're going to be... So it's going to be increasing, decreasing, increasing, decreasing. At the end of the day, what's going to happen? It's just alternating. It's not... Yeah. Basically, the current's just going to be alternating. So let's write alternating here. Let me write that nice. Alternating. Done. Next one. Moving from position 1 to position 2, we're going to have to draw the EMF. So, all right. Let me rub this out. All right. Have a look at this. So let me just copy this and basically duplicate this. Yeah. Let me duplicate it again. Right over here. So you remember in that, because, this is what the field line pretty much looks like. So if I basically draw this loop in a more color, dark color. So if I draw it a nice more color to show it. That's not really helping. Come on, draw a square for me. Basically, here's the square. Basically, this is our square. This is our actual loop. And what's happening is, all we've done is we put in from going from position 1 to position 2. Is there a change in flux? No, it's not. It's going to be always at its maximum flux, but it's not changing. As we can see here, we're going from here. It's still in the same value. It's going to, those field lines are all passing. And because it's going at a constant velocity, basically, there is no change in flux. Basically, there's no change in flux. It's just going to be all the same. Your flux is the same value as you go down from position 2. So how would you represent this diagram? Basically, you would basically represent it. So if I take that out, you want to draw it like this. So let's think about it. And it's going to be at its maximum because it's always, all the field lines are always passing into it, basically. So we'll have a maximum flux, but it will be constant. There's no change in flux. So change in flux, time. So we can see it will look like this, basically. It will be just a positive because it's at its maximum, but it's going to stay constant. And basically, again, you just derive it. Basically, what's the gradient of it? It's going to be 0. And you multiply by it's just going to be 0 overall. So your EMF is basically going to be 0. There is no flux going to be, there is no EMF going to be produced because there is no change in flux. So basically the graph will look like just 0. And from position 1 to 2, it will look like a 0. It'll look like that. Done. So is there any induced current? Of course, there will be no induced current. If there's no voltage, there's no induced current. If there's no EMF, of course, there's no going to be current that's going to be produced. So no current. The last one, moving from position 2 to position 3. Okay, let's have a look at the next part. I'm going to basically rub... What did I do? Sorry, did I take... Yep, no current. Okay. Let me take this out and just delete it. So let's have a look at the next part. So if we're going from position 2 to position 3. So I'm going to draw again the square. All right. So imagine you have this square here now. And so what's happening is you're going from position 2. And as you're going to the right, you can see how those field lines are going to start decreasing. They're not passing through it. So what's happening is at a constant rate, your field lines, your flux is going to be decreasing at a constant rate. Remember, it's at its maximum because everything's passing through it. But then as you go to the right, more to the right, you can see it's going to be decreasing at a constant rate and then approach 0 when it reaches position 3. So basically, this is how you would want to draw it. So what's going to look like if I draw it in the EMF graph will look like this. So changing EMF, time. So it will look like this pretty much. So it started at its maximum, but it's going to be going down at a constant rate and then approaches 0. So again, remember, so what is its gradient? We can see its gradient is negative. And remember, by to find the EMF, you have to plot it by negative. So if the gradient is negative, it's going to be positive. So it's going to be basically, it's going to look like this. It's just going to be a positive straight line, constant straight line. And that's it. Done. So that's how your EMF should look like. So it's going to be just a positive value like this. And so that's it. And now we just need to see what's the current. So basically we can see that in terms of EMF, let's rub this out. Our EMF graph is much nicer to look at. So we can see that the flux was at its maximum and it goes down. So there is a decrease in flux. And so when there is a decrease in flux, we know that Lenz's law, what it said, there will be an induced magnetic field that will be in the same direction as your field line. So what's going to happen is you'll have a clockwise direction. Using your right-hand grip rule, your thumb is into the page, you will see a clockwise direction. There'll be induced clockwise direction, basically. So done. Clockwise direction. Done. Question 5. A wind generator provides a power to a factory located 2 kilometers away, as shown in figure 5, where there is a moderate wind blowing steadily. The generator produces an RMS voltage of this and an RMS current of this. The total resistance of the transmission wire between the wind and the generator is this. All right. Calculate the power in kilowatts produced by the wind generator when there is a moderate wind blowing steady. All right, so what I'm going to first draw is I'm going to draw a basic circuit because it really helps out when you draw a basic circuit and you can see everything into play. So what we have is we're going to have, of course, a basically your, in this case, you know, the wind generator it's going to create AC voltage. So this is your resistor, which pretty much means your transmission line, which has what, 2 ohms of resistance. And so now this part over here is your, I'm going to draw it as a light globe basically, but this here is your factory. That's it. And done. That's it. So we know that the wind generator is providing 415 volts, 415 volts, and it's providing a current of 100 amps. Easy. So calculate the power in kilowatts produced by the wind generator when there is a moderate wind blowing. Beautiful. So we know that power, it's voltage times current, and we so know that our voltage that our wind generator is producing is 415. And what's the current that's running through it? It's 100. So that's going to be 415. So 415 times 100. And we're going to divide it by 1,000 because we want it in kilo watts. That's going to be basically 41.5. Done. So to operate correctly, the factory's machinery requires a power supply of 40 kilowatts. So basically this here requires 40 kilowatts of power to work properly. Determine whether the energy supply system as shown will be able to supply the power to the factory when the moderate wind is blowing steadily. Justify your answer with calculations. Let's have a look at this. I'm going to bring this down here, basically. I'm going to bring it down here, and we're going to really have a look at this in detail. Now, we know, so basically what's going to happen is, so of course we're going to have power loss happening into this resistor here, or your transmission lines in this case. So how much, first, how much power are we producing from the wind generator? We were producing, we said 41.5, so 41.5 kilowatts. And how much power are we losing to the transmission line? The way you would calculate that is basically easy. We know that we have the current and we have the resistance. We know that power loss is equal to I squared over R, times R, which your current is 100 squared and your resistance is 2. So make sure that's going to be 100 squared times 2. And make sure this, by the way, this is going to give you in watts. So you want to divide it by 1,000 to get it in kilowatts. And that's going to give us 20 kilowatts of power. So basically, this is what's happened. We have 20 kilowatts of power here that's been lost to those transmission lines. So overall, are we providing that 40 kilowatts of energy? No, we're not. If we're producing this much and we're losing this much, how much is actually being given here? We're actually given, what's basically 41.5 kilowatts minus 20, that's going to be the rest that was given. So 41.5 minus that. We're only giving 21.5 kilowatts of energy to the, 21 factory, basically. And so we're not providing that 40 kilowatts of energy for it to work properly. So overall, it's not enough. So determine whether the energy supplied is shown is able to apply. It's not able. So basically, not able. We've shown it through calculations. Not able to supply. To supply as the power generated is less than basically 40 kilowatts. Easy. Done. Nice calculation. Yeah. Next question. The factory owner decides to limit transmission line energy loss by installing 2 transformers, a step-up transformer with the turns of this at the wind generator and a step-down transformer with turns of this at a factory. Each transformer can be considered ideal. So ideal means just pretty much the power between the transformer. There's no loss, basically. There's no loss of power. With the installation of the transformers, determine the power in kilowatts now supplied to the factory. All right, greatly. So we know that installing transformers, basically, it's a great way to actually decrease power loss. And so they've done a good job. So what I'm going to do basically is I'm going to take the same diagram and now I'm going to just a little bit affect some stuff about it. I'm going to change some stuff. So I'm going to duplicate it, bring it to the bottom here, and do some changes to it. So what are the changes going to be? So so we want to basically, let me rub some stuff out. Let me rub these out, rub that out. Okay. So we know that there's a step-up transformer. So let me draw. So a step-up transformer that was given to the factory. So I'm going to draw a nice transformer. Oops. I'm going to draw a nice transformer here. Like that. Basically. Like that. Alright. And then, of course, we have a transmission line. And let me a little bit move this to this way. And then, of course, we have our another transformer, which is our step-down transformer. Basically. And so this here is going to supply here. Basically here. Yep, so done. So we know, of course, the current here was what, 100 amps. So the power still loss is, this is how much still power we're generating. And we know the turns here is, was it at 1 to 10? Because it's up. Yep. And so 1 to 10, this one's 10 to 1 because it's a step down transformer. Of course, this is 2 ohms here. And yes, so we want to, okay. So let's have a think here. Basically, what's happening is that we're generating 41.5 kilowatts of power from this AC, or basically this means that it's a wind generator. And so it's going to go to this left side, so your primary side of the transformer. Because we know it's ideal, it's going to, there's no power loss. So now on this side, what do we have? We're pretty much produced the same power, 41.5 kilowatts to this side here. Now there's a problem. Of course, we're going to have some loss of power because there's transmission lines. Of course, there's going to be some power loss. And so we need to calculate that power loss. So the way I would do it is, because we have the current in the primary circuit, let's find it in the secondary circuit here. To do that, basically we know the turn. So it's just going to be NP over NS, nice, over NS is equal to your IS over IP, your current. So your number of primary is 1 to 10, and your secondary, so basically it's your, in the secondary there will be basically 10 amps of current. So we've calculated that. So I'm going to put this a little bit on this side. I don't want this to be too much here. I'm going to put it right over here. All right, so let's have a look. So if it's that much, so let's calculate the power loss that's going to happen to this transmission line. So we know that power loss is what? I squared, so 10 squared times your resistance. So that's going to give me 10 squared times 2. That's going to give me 200 watts, but I'm going to divide it by 1,000 to get it. So it's going to give me 0.2 kilowatts of power loss. So basically there is 0.2 kilowatts of power loss there. So if we're providing here 41.5, there's going to, of course, we're going to minus this because that's how much it consumes. So now what's going to happen, what's going to be given here? Here, it'll be given is just 41.5 minus, so 41.5 minus that. In this circuit here, we know that they will be providing now 41.3 kilowatts. Now, because again, it's ideal, so the power will be the same here. And so whatever, so overall, this much power is going to be given to this. Now, that's great. Can you see how this power here is greater than the power that we need? This is good. So we've gone above and the average. We've gone and we've hit our threshold. So like we've met that threshold. So there's, the factor is going to work properly, basically. So that's great. And so it's just saying, yeah, what determine the power that's supplied to the factory. Basically, it's 41.3 that's going to be supplied to that factory. So 41.3 kilowatts. Done. Question 6. Figure 6 shows a simple alternator consists of a rectangular coil of area of this and 200 turns, rotating in a uniform magnetic field. The magnetic flux for the coil in the vertical position is shown in figure 6 is this. All right. Calculate the strength of the magnetic field in figure 6 show working out. Beautiful and easy. So we know that your flux, let me write that down. So flux is your area times your magnetic field strength. So we know what was our flux? It's 1.2 times 10 to the power of -3. What's our area? They gave us 0.06. So 0.060. And your magnetic field strength, which we want to calculate. Beautiful. So 1.2 times 10 to the negative 3, 0.060. So that gives me 2.0 times 10 to the power of 2 Teslas of magnetic field strength. Is that right? 1, 2. Yep. Looks good. Beautiful. Next question. The rectangular coils rotate at a frequency of this. Calculate individual average induced EMF produced in the first quarter of a turn. Begin the quarter with the coil in the vertical position shown in figure 6. Beautiful. So for a quarter of a turn, there will be induced magnetic flux because we're going from a maximum to 0. So there's going to be a basically a EMF produced. And so this EMF produced is calculated using this formula. So N, your change in flux over change in time. So basically, what do we know about time? How do we calculate the time? So we know that period, basically period, so T, your period is 1 over your frequency. So your frequency is 1 over 2.5, which is 1 over 2.5. So basically period, what period tells you is it tells you how long does it take for a full rotation. But remember, we're only going for a quarter of a turn. So imagine dividing that by 4. So your time is actually 0.1 seconds. That's how long it takes for a quarter of a turn. So luckily we've got our change in time. So now putting everything that we've learned, so EMF, it's going to be, our turn was 200. Was that right? Yep. We've calculated, what about our flux? They said it was 1.2 times 10 to the power of, so 1.2 times 10 to the power of negative 3. Was that right? Yep. Divided by your change in time, which is 0.1. So that gives me 2.4 volts. Done. Question 7. Kim and Kelly are experimenting with trolleys on a ramp inclined at 25 degrees as shown in figure 7. They release a trolley with a mass of 2 kilograms from a top of a ramp. The trolley moves down the ramp through 2 light gates and onto the horizontal frictionless surface. So if the horizontal surface is frictionless, it means that there's probably friction in this ramp. Kim and Kelly calculate the acceleration of the trolley to be 3.2 using the information from the light gates. Okay. Show that the component of the gravitational force of the trolley down the slope is 8.3. Beautiful and easy. So let's have to really understand what's happening here. So I'm going to draw probably kind of a big diagram to show what's happening. This is one of my favorite kind of topics. Yeah, so basically we have an angle here, and that angle is what? 25. So I'm going to draw the block. Let's just draw a block. This block here, I'm going to move it. Basically, oops, I'm going to move it here. Like that. Nice. And so this block is going to have, of course, a force of gravity. That's going to be vertically down. Of course, it's going to have a normal force, but who cares about the normal force? But only because we want the gravitational force. So this normal force is what? We know it's going to be 2 times 9.8. What's 2 times 9.8? Because it's mass times gravity, 19.6. Basically, it's 19.6. And so if we break it down to its components, if you can break this down to its components, where we know this angle here is the same as the angle 25, what do we have here? We want to calculate this here over here. That component of the gravitational force is what makes the trolley go down, basically. And that's what we're trying to calculate. And so it's basic trigonometry. So we know we're trying to find our opposite and we have a hypotenuse. So we're going to use basically sine our angle 25 is opposite. What's our opposite? So x over 19.6. So our x is 19.6 sine 25 degrees. So it's going to be 8.3, basically. 8.3, yeah, we did get 8.3. 8.3. That's it. 8.3 newtons. Done. That's good. So assume that on the ramp there is a constant frictional force acting on the trolley and opposing its motion. Calculate the magnitude of the constant frictional force acting on the trolley. Of course, we said that there was going to probably, because you know how there's friction here, because they said that it was not, frictional force on that trolley. So, okay, so let me break everything apart. So the force that we just calculated is the only force that we're going to need because that's what accelerates it. So let's rub everything out. So we know that this is the force that accelerates it down the plane, and it was 8.3. And we said that there's, of course, a constant frictional force that's going to oppose its motion, which is what we're trying to basically calculate. I'm going to call it F for friction. So your net force, so F net, is the addition of these two forces. We're going to take down as positive, by the way, because it's going to be going down. So it's going to be 8.3 minus your frictional force. And your F net is what? Basically, it's mass times acceleration. So mass, what's our mass? It's 2. Your acceleration, they have given it 3.2 is equal to 8.3 minus F. So F is 8.3 minus 2, 3.2. Done. So it's going to be 8.3 minus 2, 3.2. So it's going to be 1.9 newtons. Done. B. When it reaches the bottom of the ramp, the trolley travels along a horizontal frictional surface at a speed of this until it collides with the stationary identical trolley. The two trolleys stick together and continue in the same direction as the first trolley. Calculate the speed of the two trolleys after the collision, show your working, and clearly state the physics principle that you have used. Alright, so let's have a look. Okay, beautiful. So I'm just going to draw a diagram here. The same diagram, but in the more basic collision. So basically we have... let me draw it a nicer. So you say, we have our blocks here. Really, why is it not really drawing it for me? Okay, here's nice blocks. So like that. Let me just draw those. All right, so these are our blocks basically. And I'm going to duplicate 2, basically. So this one's the one that's moving to the left because it's just gone down this thing and it's now going to hit this stationary trolley. So basically, I'm going to call this M1 and this here M2. So we know that the velocity, this is going to be U1, and we know that we're going to take basically the direction of the left positive because that's where the direction of motion is. So we're going to take this as U1, and that's going to be 4 meters per second. And we know this is going to be 0 because it's stationary. And so after they collide, they stick together, they said. So imagine basically drawing a bigger mass like this, like that. And it's both their masses combined, so M3, which is both of their masses combined. And of course, it's going to be moving to the left at some velocity. We're going to call it V3. And that's it. So to make an expression, what are we going to do is the main thing the physics principle that we're using is the conservation of momentum. So conservation of momentum. So let's make a formula. So we know that basically M1 U1 plus M2 U2 must equal to M3 V3. So what's M1? So 2. U1 is 4 plus M2. Remember, because they're identical, they have the same masses. So 2. U2 is 0. So that's nothing. Equals M3, which is the addition of both masses. So basically 4 and V3. And that's what we're trying to calculate. Basically, V3 is 2 meters per second. Done. Easy. All good there. The second, determine with calculation whether this collision is elastic or inelastic collision. Show you're working out. What a beautiful, nice question. It always comes up in exam and it's very easy to get full marks. So for elastic collisions, the kinetic energy before must equal to your kinetic energy after. That's the condition that for an elastic collision to happen. So let's check if this pretty much collision was elastic. So what's the kinetic energy before? Let's calculate that first. So it's going to be half mv squared, so half mass of m1, basically 2. What was the velocity it was going? It was going at 4. Wait, was it going? Yep, 4 squared. Plus, the other one has no kinetic energy because it has a velocity of 0. So overall, this is what? your energy is just 16 joules. That's your kinetic energy before. So what's then the kinetic energy after? It's going to be half. The mass, it's going to be, because it's both of their masses, so it's going to be 4. Their velocity that they're traveling is 2 squared. So basically it's 2, 4 is 8 joules of energy. So there is a, basically they're not equal. We can see that the energy before, your kinetic energy before and your kinetic energy after are not equal. So there was some energy lost. So that tells us it's inelastic. So as KE before is not equal to kinetic energy after, this is an inelastic collision. Done. Question 8. A Formula 1 racing car is traveling at a constant speed of this, so 40 meters per second, around a horizontal corner of radius that. The combined mass of the driver and the car is that. Figure A shows the front view and the figure shows the top view. Beautiful. A. Calculate the magnitude of the net force acting on the racing car and the driver as they go around. Beautiful. So we know that the net force for any circular motion is mv squared over r. So what's the mass? It's 800. What's the velocity? 40 squared divided by the radius. So the radius at the traveling is 80. So that's going to be 840 squared, 80. So that's going to give us 1.6 times 10 to the power of, so 1, 2, 3, 4. Is that right? So 1, 2, 3, 4. Yep, 4 newtons. So 1.6 times 10 to the power 4 newtons. Done. B. On figure 8b, draw a direction of the net force acting on the racing car using arrows. Beautiful. So we know it's going through circular motion, and we know basically that the net force is always acting towards the center of the circle. That's your F net. Done. Easy. Explain why that racing car needs a net horizontal force to travel around the corner, and state what exerts this horizontal force. Okay, basically let's understand what's this net force. Why do we need this net force? Why does it have to be on the right, especially in this position? It's because if your velocity is going down, can you see how they are perpendicular? Basically, we need that centripetal force, that F net, to be perpendicular. So this is what changes the direction of the car. So when the car is here, the net force is going to be up and it's going to go like this. So it's always that overall centripetal force is changing the direction of motion of that car. Basically, that's why we need that, basically, that net force, that F net in the horizontal direction. And so what is that F net? What is actually creating that F net? It's basically this. It's the frictional force. Basically, it's just the frictional force between the tires and the floor that it's running out. So what's happening basically is that the floor is pretty much pushing up on those tires, and that causes friction, and hence that is what is our F net. So basically, F net is the frictional force between the tires and the floor. That's what causes this F net to happen, basically. Easy. So let's write that down. So we can say what we were supposed to say is, okay, we said we need to say the centripetal force. So it's only 2 marks. So the centripetal force is perpendicular. It's always going to be perpendicular to the direction of motion. To the direction of motion of the car. And it changes the direction of motion, basically. That's what we say. So direction of motion. Done. And also so it says state what exerts this force. It's basically the force. So the force on the car is due to friction. Between the ground and between the ground and the tires. And so where the ground pushes up on those tires. So ground pushes up on tires. That's what's really happening. That's it. I think that's, yeah, you don't have to go in detail, basically. Just 2 marks. Question 9. A star is transforming energy at a rate of this. Explain the type of transformation involved and what effect, if any, the transformation would have on the mass of the star. No calculations required. What a beautiful question. I think it's not a lot of information they've given us, but you should straight away realize that if a star is transforming, a star is like our sun. It's this big thing, like a star. And so explain the type of transformation involved and what effect. You should realize that this is fusion, nuclear fusion. We know our sun. Let me draw a sun here. Oh, that's not ugly, Let's draw a sun. Let's draw this sun here. Basically, what's happening in our sun is that it's radiating energy, heat energy in this form. But how? You might question. So this actually, basically, it's called this reaction, this type of transformation, it's called nuclear fusion. And what's happening is when you get 2 helium, it's like when you get 2 helium inside our sun in this example, we got 2 helium atoms basically colliding with each other, forming a different nuclei, which is like helium. And with that, it will release some energy. And that's what the energy is basically releasing. That's what energy is releasing from the sun. But, what's really happening is, this is what's happening. But, so we can see that mass is changing, but it's releasing energy. So, what's that question? So basically, this is what's happening. So Einstein stated that mass, this is called a mass-energy transformation. And so mass and energy are kind of related to each other. So as the sun, basically, why is that energy forming from the sun? It's basically because mass is lost. So the mass, in the sun, mass is being lost and it's being transformed to energy. So Einstein, his formula, E equals mc squared, basically states this. It gives it in a nice description. So we can see that mass is what? Energy over c squared. In other words, mass is proportional to energy. It tells us that when mass is lost, so when mass is actually lost, energy is given. So for example, in the sun, we can see that energy is lost from the sun. If energy is lost, this tells us that the mass is being lost. So actually, if you look at the overall, the mass of the sun is getting smaller and smaller, but in such little intervals, by the way, because the sun is very large. But we can see that the mass should be lowering and lowering, getting smaller and smaller. So basically, did we answer it? So we said it's told us explain the type of transformation. So the type of transformation is basically a nuclear fusion of a star, and that is basically just a mass energy transformation or a energy mass transformations, vice versa, and if any, the transformation would have on the mass of the star, well, basically, energy is being released. So energy is being decreasing. Energy must also, the mass also of the sun or the star must decrease also too. So that's what basically it is. So let's write that down. So the star pretty much goes through nuclear fusion. That's the kind of reaction that's happening to it, which, because it's saying what are the transformation, which is pretty much, which is a mass energy transformation. Energy transformation. Basically, and so as the energy releases, the mass of the star decreases by EMC squared, Einstein's famous formula. Basically, I think that's all you need, because it's 2 marks. It's not that high, but I think a lot of students might forget about this. This is very important. Remember, have it on your summary sheet. This is where sometimes little information is needed, because it's not very focused on, basically, like the energy transformations of stars. But yeah, the star overall goes through nuclear fusion, which is basically a mass energy transformations. And yeah, we know that the mass of the star decreases as time. So question 10. Physics student uses a 10-ball launcher on a level outdoor oval on a windless day to investigate projectile motion as shown in figure 9. Assume that the tennis balls are launched from the ground. The tennis ball launcher can be set to project tennis balls at a speed u between 8 to 30. So you can actually change the speed and at angles between 10 to 20. All right, so you can change the angles and the speed. Standard tennis ball of mass 56 grams are used. The students measure the range of the projectile tennis ball at a fixed speed for various angles. The variables in this experiment that can be classified as control, dependent, or independent. Complete the table below by providing one variable from the experiment for each classification. Basically, easy. So we know a control variable is the variable that's not changed. And that's, in this example, it's like the mass of the ball, because we know it's fixed, it states. So a control variable in this case is the mass of ball. The dependent variable is the variable that changes. It's the variable that we're first measuring, and it changes due to the independent variable. So what are we trying to measure? Basically, we're trying to measure the range. Your independent variable is the variable that you rectify or you're changing. Basically, it's not like, it's basically what you're changing. So the things that we can change is both the angle and basically I'll just say angle and the speed of the ball, but I'll just say one, so angle. That's it. That's easy. So the students set the tennis ball launcher to project tennis balls at a speed of 25 meters per second. They vary the angle between 10 to 20 and measure the range. Beautiful. The students repeat each experiment at each angle 3 times and determine the average range. The results are shown in table 1. So we have the angle and the average range. Beautiful. The students determined that the uncertainty of the measurements of the range is plus or negative 1. All right. On the grid provided below, plot the data from table 1. All right. Add scales to each axis. Insert appropriate uncertainty bars for the range for at least 3 data points and draw a smooth curve of best fit. That's 6 marks. All right. Let's do that. So launch speed, the horizontal, okay, so your independent variable. How much is it going, your launch speed? So, no, your launch angle, sorry, your launch angle. Your launch angle is going by 10, so 10, 20, 30. Beautiful, so 10, 20, 30. We're going to go by 5. So, like, for example, each interval here, it's going to go by 5, I want to say. So, 5. Basically, that's going to be 5, 10, 15, 20, 25. So, that's going to be 25 here. That's going to be 50. That's going to be 75. That's going to be 100. That's what I'm thinking would be a good interval for that. The next one, what is that? So it's going by, your average range is going by, the max is 40. And I'll say, by looking at this, if I go 2, 4, 6, 8, 10, 10. Yes, so we can actually go by 2s. So 2, 4, 6, 8, 10. So that's going to give us 10. That's going to give us 20. That's going to give us 30. And that's here going to give us 40, which is our max. That's all we need. So basically going by 2s in this case. All right. And now let's plot those points, basically. Okay, so 10, 17. So angle 10, 17. So because it's going 10, 17 is 2, 4, 6 here. At this point, beautiful. 20, 30, so 20, 30, so here, basically, yep, so 30, so wait, range is 30, angle's 20, beautiful, 30, 37, 25, 30, so wait, 5, 10, 15, 20, 25, 30, so 30, 27, 37, sorry, so 2, 4, 6, that, right over here, so that's 37, and 40, 40, so basically that's 40, 40 here, 50, 40, so basically here, that's, yep, 50, yes, 60, 36, so 60, 36, so 60, 36, so 2, 4, 6 there, right over here, yep. So 60, 36, was that right? 60, 36, 2, 4, 6. Yep. 70, 29. So 70, 29. 2, 4, 6, 8, 29 here. Right over here. Beautiful. 80, 15. So 80, 15. 2, 4, so here, right over here. That's 15 because 80. 85. So 75, 80. Yep, so 75, 80. Is that right? 80 to 15. 2, 4. Yes, that's it. And we know that we want to add those uncertainty, which is plus or negative 1, which is basically, I'm going to write it in this color. So that, like that. That's going to be that, like this. Like that. Like this. Basically, these are the uncertainty because plus or negative 1. And so that, like that. And that, done. We are nearly done. So we've plotted the graph, the data, the scales. We've also done scales, insert uncertainty bars, and draw a smooth curve. At the end, you just draw a smooth curve. So I'm going to draw basically, it looks like a parabola basically. It's going to pass through all these points like this. Nicely walks through those points basically. And yeah, it does look like it's passing through all those points. Is that right? So there. Let me draw a nicer maybe one. So let me draw it like that. And like that. Maybe that's it. There we go. So a little bit getting into, okay, perfect. That's it. That's a nice smooth curve. So from the graph and part B, estimate the maximum range and the angle that gives that maximum range. Beautiful. So maximum range is this peak over here, basically. So we can see that it's 41. 41, did you say? 41.5 or 40.5? I'll say 41. Maybe my graph's not the best, but I'll say 41. And the angle for the maximum range is basically over here, which is 45. Yep. 5, 30, 35, 40, 45. 45, done. Done. Question D. The students think that the air resistance on the tennis ball may affect the maximum range. They decide to compare their data to the theoretical range achieved when air resistance is ignored. So using the range formula, calculate the theoretical range of the projectile launch at the initial speed of this, angle of this, and choose that. Beautiful. So sub those all into a formula. So 25 squared sine 2 times your angle, all being divided by your g, which is 9.8. And that's going to give us our theoretical range. That gives me 55 pretty much. So 55 meters approximately. Yeah, that's our range. Is this the last question? Yes. Evaluate whether the effect of air resistance can be ignored by the students when analyzing their data. Justify your answer. So if we got the theoretical yield to be 55 meters and the actual theoretical range to be 55 and the maximum range is 41 in our actual data, this is such a big difference. What's the difference? So 55 minus 41, that's 14 meters difference. That's a big difference because we cannot ignore air resistance. We really can't because you got to remember that our uncertainty in the range is plus or negative 1. So we've gone above our uncertainty. We've gone above our maximum uncertainty. We're like 14 meters difference. So you really cannot ignore air resistance in your calculations. That is such a big difference, yeah. So evaluate whether the effect of it can be ignored by the students when analyzing. You cannot ignore it, straight out. The difference between the theoretical range and the measured, it's like, so it's 14, yeah? 55 minus 40. It's 14 meters. This is too large. And so, hence, it cannot be ignored. Your air resistance cannot be ignored because it goes above our uncertainty maximum, which is a plus or negative 1. So, let's write that. 3 marks, wow. Let's write that down, basically. All right. So, the difference between theoretical range and measured is 55 minus 41, which is a 14 meter difference, basically. And so we know that this is too large. and cannot, let me put a comma there, cannot be ignored because it goes above our uncertainty. Which is basically, was it? It was plus or negative 1 meter. It goes above that, and so hence air resistance. What am I doing? Air resistance cannot be ignored. And that is it for this exam. I hope you guys learned something with this video. Please make sure to like and subscribe for more future videos like this. And yeah, please make sure you take care of yourself. Have a great day, guys. Bye-bye.